Hi there, civil engineers of the future. I'm your instructor, Daryl J. Mendros-Balbin. In this video, I will discuss a sample problem in the analysis of gravity dams. A masonry dam of a trapezoidal section with one face vertical is 0.6 meter thick at the top and 3.0 meter at the bottom. It is 6.6 meter high and has a horizontal base. On the inclined face, water stands 4.5 meters deep. Assume a specific gravity of 2.4 for the dam, and hydrostatic uplift varies from 60% at the hill, that is 60% gamma h at the hill, to 0 at the toe. We need to identify the different forces acting on the dam. For vertical forces, we have weight of the dam. And for the weight of the dam, we're going to subdivide the trapezoid into a rectangle and triangle. And for the weight of the rectangle, we have weight 1. For the triangle, weight 2. We also have the weight of water in the upstream side, Fv, or the vertical component of hydrostatic force. In order to solve for Fv, we need to draw a vertical line from this point up until the water surface. And this area enclosed, which is a triangle, will be considered. But first we need to solve for this base of the said triangle. Let's call that base of the triangle base A. And to solve for base A, we consider similar triangles, this small triangle and this big triangle. So we have base of the small triangle A over altitude of small triangle is equal to base of the big triangle over altitude of the big triangle. And if we try to calculate for A, that will be 1.64. We also have the hydrostatic uplift U at the bottom of the dam. And to solve for hydrostatic uplift, we need the area of this pressure diagram, which is again a triangle. But first we need to solve for the altitude of that triangle, which is 60% gamma h. So we have 0.6 times gamma of water, 9.81. Our h is the height from the bottom of the dam until the water surface, which is 4.5. So that the altitude of the triangular pressure diagram is 26.487 kilopascals. Those are the vertical forces acting on the dam. For horizontal forces, we have Fh, or the horizontal component of hydrostatic force. To solve for Fh, we need to consider the vertical projection of the submerged portion of the dam. So if we project the submerged portion of the dam vertically, that will be a rectangle. And we will be considering 1 unit or 1 meter length of dam perpendicular to the sketch. So the width of the rectangle will be 1 meter. We need to identify H bar, which is the location, which is the distance, vertical distance from the center of gravity until the water surface. So that is simply 1/2 of h, which is 4.5 meters. So h bar, the vertical distance from CG to the water surface, is 2.25 meters. And we also need to determine the location or the center of pressure. The center of pressure is where FH acts. And you have to remember this: for rectangle, you don't need to solve for eccentricity E. You just have to remember that for rectangles, the center of pressure is always located h/3 from the bottom. So that is 4.5 divided by 3. The center of pressure CP is located 1.5 meters from the bottom of the rectangle. So that is the horizontal force acting on the dam. Next, we try to identify the toe and heel of the dam. For the toe is the pivot point of the dam. It is located on the downstream side. So the left side of the dam is the upstream side, and the right side is the downstream side. Therefore, this will be the toe of the dam, the pivot point or the downstream edge. And for heel, that is simply the opposite of your toe. Your heel is located on the upstream side of the dam. So this is the location of your heel and toe. For letter A, we need to find the vertical component of the foundation reaction, Ry. We need to calculate the magnitude of the different forces acting on the dam, starting with weight 1, which is for the rectangular portion of the dam. Weight 1 is equal to gamma volume, where gamma is the gamma of the dam, and that is equal to its Sg 2.4 multiplied to the gamma of water 9.81. And the volume will be area of the rectangle, which is base 0.6 times height 6.6, and we multiply that area to 1 meter length perpendicular to the sketch. Therefore, weight 1 is equal to 93.23 kilonewtons. For weight 2, that is considering the triangular portion of the dam. Gamma of dam is 2.4 times 9.81. And for the volume, we multiply the area of the triangle, which is 1/2 base, 2.4, height, 6.6. And once again, multiply that area to 1 meter length perpendicular to the sketch. W2 is equal to 186.47 kilonewtons. For FV, that is also gamma volume, but our gamma here will be gamma of water 9.81, since we're dealing with the weight of water. And the volume will be area of this triangle, which is 1/2 base 1.64, height 4.5, times, once again, 1 meter length perpendicular to the sketch. FV is equal to 36.2 kilonewtons. And for the last vertical force, hydrostatic uplift U, that is simply the area of the triangular pressure diagram multiplied to 1 meter length perpendicular to sketch. For the area of the triangle, we have 1/2 base, 3 meters, height 26.487. Therefore, U is equal to 39.73. And for the horizontal force FH, that is simply gamma H bar area. Our gamma of water is 9.81 and our H bar is 2.25 meters. Our area is the area of the vertical projection, which is base 1 times height 4.5. Therefore, FH is equal to 99.33 kilonewtons. Now we're ready to solve for Ry and Rx. For Ry, which is the requirement for letter A, that is simply summation of Fy, and that is equal to W1 plus W2 plus Fv minus U. So Ry is equal to 276.17 kilonewtons. And that is our answer for letter A. And for our Rx, that is simply the summation of all horizontal forces. And we only have one horizontal force, FH. So therefore, Rx is equal to FH, which is 99.33 kilonewtons. For letter B, we need to find how far from the toe will the force, referring to Ry, intersect the base. This is simply x bar, which is the location of Ry from Rx. If we try to sketch Ry and Rx, this will be Rx. And from the toe, we have Ry. And the distance from the toe to Ry is x bar. And to solve for x bar, we have the formula Rm minus Om over Ry, where Rm is the righting moment and Om is the overturning moment. For the overturning moment, this is created by the forces acting in the dam that tend to overturn the dam about the toe. So these forces are the uplift, hydrostatic uplift, which turns to overturn the dam about the toe, and also FH. It also tends to overturn the dam about the toe. So for OM, we need to take the moments of FH and U about the toe. So meaning we need to determine the moment arms of FH and U with respect to the toe. For FH, with respect to the toe, this will be its moment arm, which is h over 3, the location of CP from the bottom, and that is 1.5 meters. And for U, with respect to the toe, the moment arm will be, since this is a triangle, it will be 2/3 the base of the triangle. So 2/3 of 3. Or that is simply 2 meters. So the location of U with respect to the toe will be 2 meters. So for overturning moment, that is simply equal to FH times 1.5 plus U times 2. So substituting, our overturning moment OM is equal to 228.46 kilonewton meter. And for RM, righting moment, that is the opposite of overturning moment. Righting moment is created by the forces that tends to right the overturning moment. Forces that try to or tend to right the overturning moment. How do these forces right the overturning moment? They tend to keep the dam in its place. So these forces that create righting moment are FV, W2, and W1. So we also need to determine the moment arms of these three forces with respect to the toe. So for W1, the moment arm with respect to the toe will be 1/2 of 0.6, so that will be 0.3. For the moment arm of W2 with respect to the toe, that will be 0.6 plus 1/3 of 2.4. So that is 0.6 plus 2.4 over 3. And for the moment arm of FV with respect to the toe, that is simply 3 meters minus this distance, which is 1/3 of 1.64. So this is 3 minus 1.64 divided by 3. So RM is equal to W1 times 0.3 plus W2 times 0.6 plus 2.4 over 3 plus FV times 3 minus 1.64 divided by 3. Substituting, RM is equal to 377.84 kilonewton meter. Now that we have solved OM and RM, we can solve for X bar. Substituting now, RMOM and your RY, X bar is equal to 0.541 meter, which is the location of RY from the toe. For letter C and letter D, we need to find the factor of safety against overturning and against sliding, as showing mu is equal to 0.51 respectively. FO, or factor of safety against overturning, is equal to righting moment over overturning moment. These two moments were just solved a while back, so we simply substitute. FO is equal to 1.65. And FS, or factor of safety against sliding, is equal to mu s Ry over Rx. Again, we simply substitute. Fs is equal to 1.42. For letter E, we need to solve for the intensity of pressure at the toe. But is the pressure at the toe maximum or minimum? To answer that, we need to solve for E which is the difference between b over 2 and x bar. Now there is a significance to the sign of e. Let me try to illustrate. So if we have the base of the dam and divide it to 2, so that we have b over 2, b over 2. This is the toe based from the problem, and this is the heel. For the first case, we have x bar, which is the location of your ry from the toe, is less than b over 2. This means that e has a positive value. And this means that the maximum pressure occurs at the toe. And for the next case, we have the base of the dam still divided into 2. Same location for toe and heel based on the problem. And this time, x bar is greater than b over 2. This means that E has a negative value in this equation. And this means that maximum pressure occurs at the heel. So again, if E has a positive value, maximum pressure occurs at the toe. And if E has a negative value, maximum pressure occurs at the heel. And we have a positive E if x bar is less than b over 2. And we have a negative E if x bar is greater than b over 2. So based on our problem, if we substitute our values, we have a positive value of E. This means that the pressure at the toe is maximum pressure. So now that we know that the pressure at the toe is maximum, we can now solve for its magnitude. We need to solve for b over 6 and compare it to E. 0.959 is greater than 0.5, or E is greater than b over 6. Now, what is the significance of the comparison between E and b over 6? Let me try to illustrate. So we have the base of the dam, and we're going to divide it into 3. So that we have b over 3, b over 3, and b over 3. And in the middle third, we divide it into 2 so that we have b over 6 and b over 6. Now based on the problem, this is the location of the toe and the location of the heel. And from the middle, we have b over 2. Now, based on our comparison between E and b over 6, it says that your E compared to b over 6 is greater. This is now your x bar, which is the location of your ry from the toe. So this is ry, and we can see that ry is outside our middle third. So if E is greater than b over 6, ry is outside the middle third. So E is greater than B over 6. Ry is located outside the middle third. Now, if this is the case, we will have a triangular diagram. And this will be the pressure diagram. A triangular pressure diagram, wherein this is your maximum pressure and this is your minimum pressure. The magnitude of minimum pressure is 0. The magnitude of maximum pressure is 2Ry over 3x bar. Now, since pressure at the toe is maximum pressure, we substitute, and our maximum pressure, or pressure at the toe, is 340.32 kilopascals. Now we also have another case wherein our E is not greater than B over 6 but less than or equal to B over 6. So let me try to illustrate again. So we have the base of the dam and we divide that into 3. So this will be B over 6. Based on the problem, this is the location of the toe and heel. Now if we have also B over 2, now this time E is less than B over 6. So this will be the location of your Ry. Ry will be inside the middle third. So this is the case when your E is less than B over 6 or E is even equal to B over 6. So what will be the shape of our pressure diagram? So here if E is greater than B over 6, we have a triangular pressure diagram. But if E is less than or equal to B over 6, just like illustrated, our pressure diagram will be trapezoidal. So we will have a trapezoidal pressure diagram. In this case, Ry now is inside the middle third. So if we try to illustrate now, so we will have a trapezoidal pressure diagram, wherein this will be Q max and this will be Q mean. Wherein Q max or mean is equal to Ry over B times 1 plus negative 6 E over B. 6E over B. Now, if you are solving for maximum, you use the positive. If you're solving for minimum, you use the negative. So here, Ry is inside the middle third. So again, we have a triangular pressure diagram if E is greater than B over 6, wherein our Q maximum is given by this formula and our Q minimum is simply 0. But if E is less than or equal to B over 6, this is the value of Q maximum and Q minimum. In this case, Ry is outside the middle third, whereas in this case, Ry is inside the middle third. For F and G, we need to calculate the total force of water on the upstream phase and the total force acting on the dam. For the total force of water on the upstream phase, that is simply the resultant or total hydrostatic force, which is the square root of Fh squared plus Fv squared. Substituting, F is equal to 105.72 kilonewtons. And for the total force acting on the dam, that is R, which is simply the square root of Rx squared plus Ry squared. Substituting, we have R is equal to 293.49 kilonewtons.